All right, we've been working with dot products recently, and now it'll be helpful to discuss the properties of dot products because eventually we'll generalize this concept of a dot product, and it'll be pretty neat. So first, let u, v, and w be vectors in Rn. So those three vectors have n elements, and let c be a scalar. The first property, and there'll be four properties, the first property is the order of the dot product doesn't matter. So u dot v is equal to v dot u. And we're going to prove all these four properties in a little bit. But first, we'll just list them. The second property is that u dotted with v plus w, well, that u can be distributed. So that's equal to u dot v plus u dot w. All right. Property 3 is that if you have a scalar multiple c being multiplied by u dot v, well, that scalar multiple can go in front of the u first or in front of the v first. So it doesn't matter when you multiply that scalar multiple c. All right, and the last property, property 4, kind of has two pieces here. If you have v dot with itself, so v dot v, that will always be non-negative. So it's greater than or equal to 0. The only time it's equal to 0 is if the vector v is the 0 vector. And so we have v dot v is equal to 0 if and only if v is equal to 0. So the if and only if means it goes both ways. So if v dot v is equal to 0, then that means v is 0. And if v is 0, then that means v dot v is equal to 0. So the if and the if then statement goes both directions for the if and only if. So those are four properties of dot products, and we'll prove these in a little bit. Now, these are actual properties of the dot product. But first, in stepping in the direction of generalizing this concept, what we need to realize is that a dot product is a function that assigns a real number u dot v. Right? U dot v is just a number. It assigns that number to each pair of vectors u and v. Right, so you can think of it just like an ordinary function, like f of x is equal to x squared. Well, that's a function that if you input a number, you'll get another number assigned to that number. Right? Inputs and outputs. You can think of a dot product just like that. Input vectors u and v, and then apply the function, which we're calling the dot product, and you'll assign a number to that pair of vectors u and v. Now, a dot product is just one particular way to assign a real number to a pair of vectors. And we're going to generalize this idea to have more than just this one way. The one way we have right now is multiplying corresponding entries and adding them up. Right? That's a dot product. We're going to generalize this idea to be more than just that one particular way of assigning a number to a pair of vectors. Now, the generalization of the idea of a dot product is what we call an inner product. So what is an inner product? Well, again, let u, v, and w be vectors. This time just in a general vector space v. It doesn't have to be the vector space Rn. So we'll be able to look at all sorts of vector spaces. And let c be a scalar. An inner product is a function that assigns a real number. And this real number this time will be denoted with these angled brackets. And we call this the inner product between u and v. So before it was u dot v. Now the angle brackets means inner product of u and v. So we're assigning that number, it's just a number, to each pair of vectors u and v and satisfies the properties below. And we'll have the same four properties. We're just going to use our new notation, which denotes this generalized idea, which we call inner product. So the first one is that the order of the inner product doesn't matter. So the inner product of u and v is equal to the inner product of v and u. All right, so the order doesn't matter. The second property, the inner product of u with v plus w is equal to the inner product of u with v plus the inner product of u with w. All right, so that's like that distribution property of dot products being generalized to inner products. All right, property 3, if you have a scalar multiple c, and it's multiplying the inner product u with v, then that scalar multiple can be multiplied by the u first or by the v first, or just after the inner product was done. It doesn't matter, just like with dot products. And property 4, if we have the inner product of v with itself, so inner product of v with v, that will always be greater than or equal to 0. The only time that it's equal to 0 is if the vector v is 0. And again, this if and only if works both ways. So if the inner product is 0, then v is 0. And also if v is 0, then the inner product of v with itself is 0. So the if then statement goes both ways for this if and only if. All right, now that we know what an inner product is, I'll show you that a dot product is just a particular version of an inner product. So let u be the vector u1, u2, and let v be the vector v1, v2. So that means u and v both live in R2, so our vector space here is R2. And let the inner product of u with v be defined as u1 times v1 plus u2 times v2. Right? That's just the dot product. Right? That's the dot product between u and v. But now we're using the notation of an inner product. We'll show that it satisfies all 4 of those properties. And so we're showing that this particular assignment of a number to the pair of vectors u and v is a particular instance of an inner product. And later we'll look at other particular inner products that's not a dot product. All right, let's check out property number 1. We need to show that the order doesn't matter. So the inner product of u and v is defined to be u1 v1 plus u2 v2, right? But we know we can rearrange the multiplication of numbers, right? Because u1 and v1 are just numbers, and u2 and v2 are just numbers. And multiplication, the order doesn't matter. And this is just equal to the inner product of v with u. So we satisfied the first property. Now let's look at the distribution property. So u, the inner product of u with v plus w, well, by our definition, that'd be u1 times v1 plus w1. And then we add that to u2 times v2 plus w2. Right, so that parentheses is the second vector, right? V plus w is just a vector. So that's the second vector in our inner product. And we can distribute that u1 through and the u2 through into the sum to get that result. And notice that is 2 inner products. It's the inner product of u with v added to the inner product of u with w. So we've satisfied property 2. All right, let's check property 3. So the placement of that constant multiple doesn't change the result, is what we're checking. So by definition, c being multiplied by the inner product of u and v would be c times u1 v1 plus u2 v2. And that's just from the definition of how we defined the inner product of u with v in this particular case. Now we can distribute that c through and have it being multiplied by the u1 and the u2, or we can move it to being multiplied that c by the v1 and the v2. Right? Doesn't matter, but both of those are just those 2 inner products that we're checking to see if they're equal to each other. Right? It's the inner product of cu with v, and that's the same as u, the inner product of u with cv. Right? So they're all equal to each other. So that checks off property 3. We've showed that is true for this particular inner product. And this inner product is just a dot product. And lastly, property 4, we need to check. So if you take the inner product of v with itself, it's greater than or equal to 0. Right? So by definition, inner product of v with itself is v1 times v1 plus v2 times v2, which is v1 squared plus v2 squared. We know v1 squared is always not negative, and v2 is always not negative. So that shows that it's greater than or equal to 0. Right? So we found that first part of property 4 to be true. All right. If the vector is the 0 vector, then the vector dot with the inner product of that vector with itself, right? Inner product of 0 with itself is 0 squared plus 0 squared. So we've shown that's equal to 0. Now we just got to show the other way. If v inner product with v is 0, then, well, that means v1 squared plus v2 squared is equal to 0. And this implies that the vector is 0. So we're showing it both ways, right? If the inner product is 0, then v is 0. If v is 0, then the inner product of v with itself is 0. So we've shown both ways. And that finishes proving that property 4 is satisfied with this particular inner product, which is a dot product. All right, now we'll look at another inner product that's different than the normal dot product. So this time, if we have the vectors u and v that live in R2, so our vector space is R2 in this case, again, let the inner product u with v be u1 times v1 plus 2 times u2 v2. So the only difference here is that scalar multiple 2 being multiplied by the second entries, the second elements in the vectors. All right, so first starting with property 1, the order doesn't matter is what we need to check. Well, by definition, the inner product of u with v is u1 v1 plus 2 u2 v2. And we can rearrange the u1, the v1, and the u2 v2, because multiplication order doesn't matter. And by definition, that is the inner product of v with u. So that satisfies property 1. Second property, right, the distribution property. So here is the inner product of u with the sum of v and w. Right, so by definition, that's what the inner product is. And you can rewrite that, right, by distributing the u1 through to the sum and the u2 through to the sum, and also distributing the 2 through into the sum. We realize that's just the inner product of u and v and u and w added together. So that checks off property 2. So far this inner product is satisfying the first two properties. Just got to verify the last two. So property 3, the placement of the constant multiple c doesn't matter. So by definition, this is what c multiplied by the inner product of u and v is. Now you can multiply the scalar multiple c by the elements in u first, or by the elements on v first. So it doesn't matter. And so we've shown that that's the same as inner product of cu with v and u with cv. Right? So any way you want to do the inner product, they're all equal. So that satisfies property 3. And lastly, property 4, the inner product of a vector in R2 with itself is greater than or equal to 0. So let's check that part first. So by definition, v inner product with v is v1 times v1 plus 2v2 times v2, which is v1 squared plus 2v2 squared, right? And v1 squared is always positive or 0, and v2 is always positive or 0. So that has to be greater than or equal to 0. All right. Now if v is 0, then the inner product of 0 with itself is definitely 0. So that satisfies that part of property 4. And lastly, if the inner product of v with itself is 0, then that means v1 squared plus 2 times v2 squared is equal to 0. The only way that can be true is if v is the 0 vector. So that satisfies the last part of property 4. All right, the main point here is that there is another inner product we can define that's different than the normal dot product, but it does the same thing. It assigns a number to a pair of vectors u and v, right? So as you can think of it as a function, and it satisfies these 4 properties, just like a dot product does. All right, now that we've seen 2 different instances of an inner product, one being the dot product and another one that was different than a dot product, we'll see an example here of something that's not an inner product. All right, so for u and v, right, that live in R2 again, let the inner product, at least something that might be an inner product, but we'll show it's not, let it be defined to be u1 v1 plus u2 v2 plus 1. Right, so we have this plus 1 added onto our usual dot product. We'll just look at property 3 here. So if you have that scalar multiple placement at different spots, we'll check to see if they're equal to each other. So first, let's look at c being multiplied by the inner product of u with v. All right, so by our definition of the inner product of u and v, right, That's equal to c times u1v1 plus u2v2 plus 1. So there's that plus 1 there now. And if you distribute that c through, you'll get a plus c at the end of it. All right, so remember that. Now let's check what happens if we take the inner product of cu with v. So the placement of the c is different. Well, by definition of our inner product, at least potential inner product, we have cu1 multiplied by v1 plus cu2 being multiplied by v2, and then we just have a plus 1 this time. So notice that we have a plus c and a plus 1, and so these results are different, right? If c is not equal to 1, so if, and this has to be true for any scalar multiple, so if c is equal to 3, right, these two results are clearly different. So that means we do not satisfy property 3. That means this definition that we have here is not an inner product. It's not an instance of an inner product because it doesn't satisfy property 3. You can also show it doesn't satisfy property 4 pretty quickly, because if you tried doing the inner product of 0 with itself, you would not get 0. You'd get 1. So that's another property that's not satisfied with this assignment of a number to the pair of vectors u and v. All right, now we're going to look at a pretty cool inner product. So let f and g be two functions in C bracket a comma b. So what does that mean? It means the set of all functions, all continuous functions, so that's the C, continuous, all continuous functions on the closed interval a to b. So that's what C bracket a comma b means, the set of all continuous functions on the closed interval a to b. So let f and g be in that set, and we're defining this inner product of f with g to be the definite integral of f times g from a to b, right? So you can interpret that as the area under the curve, where the curve is f times g, and we're integrating from a to b. So the area under f times g from a to b. So that's what we're defining the inner product to be. This is an inner product, and we'll show that it satisfies the 4 properties of an inner product. So property 1, order doesn't matter. Right, so by definition, that's what we have of the inner product of f with g. And the multiplication f and g, right, the order doesn't matter, so you can switch them around. And by our definition of this particular inner product, that's the inner product of g with f. All right, so we've satisfied property 1. Property 2, we're checking out the distribution property. So by definition of that inner product of f with g plus h, we have the integral of f being multiplied by g plus h. And we can distribute f through to both g and h and separate it into 2 different integrals, 2 separate integrals. And those 2 integrals are both inner products, right? One with f and g, and the other inner product f and h. So you've satisfied property 2. All right, property 3, the placement of the c doesn't matter is what we're checking. All right, so c multiplied by the inner product of f and g is defined to be c times the integral, right? But we know with integrals we can bring a constant multiple inside or have it outside, doesn't matter. So you can have it being multiplied by the f, or you can have it being multiplied by the g. All right, so we've shown the placement of the c doesn't matter for this inner product. All right, and lastly, property 4, the inner product of f with itself is greater than or equal to 0. Okay. So that's defined to be the integral of f times f from a to b. Okay. But if you have f times f, that's going to be always above the x-axis, so you always get a positive area, right? Because f times f will be a positive function. You're multiplying all the numbers by itself, so all the heights of the function are positive, right? Because you're squaring the value of f to get f times f. All right. We also have to check that if the function is 0, is the inner product 0? Well, yeah, because you'll be doing the integral of 0 from a to b, and that is 0. Right? The area under the function 0 is 0. So that's satisfied. We have to check the other way. If the inner product is 0, does that imply that f is 0? Well, yeah, because then you would have the integral of f times f, right, which is a positive function, or at least non-negative. It's actually not positive because it has to be the 0 function. Right? So if it was a positive function, then you'd accumulate area. And so we know at least f times f is non-negative, and it can't be positive because it's saying inner product is 0. So that means f has to be 0. So we've finished satisfying property 4. So we've shown that this inner product, this particular inner product, f times g, satisfies all the properties. So it really is an inner product, unlike the previous one we just showed where it was an inner product. This one we've shown it says all 4 properties. We're going to be utilizing this inner product a lot later on because we can do pretty cool, pretty neat stuff with it. Now that we have generalized the idea of a dot product into an inner product, we're also going to generalize the concepts corresponding to dot products into these concepts for inner products. So from before, we looked at the length of a vector, in other words, the norm or magnitude of a vector in our vector space, and we defined that to be the square root of v dotted with v. Okay, so we looked at this in a previous video and saw geometrically why that made sense. Another concept was the distance between 2 vectors was defined to be the length of u minus v, which can be rewritten as the square root of u minus v dotted with u minus v, right? By understanding the definition of length from above. And also orthogonality of 2 vectors means that u dot v is 0. And it works both ways. If u dot v is 0, then that means the vectors are orthogonal. So those are our 3 main concepts that we developed with dot products. So the idea of length and distance between 2 vectors and orthogonality. We can generalize these ideas with inner products. So now more general is the length of a vector is the square root of the inner product of v with itself instead of v dotted with itself. The distance between 2 vectors is the same thing, the length between u minus v, but now using what we mean by length, it's the square root of u minus v inner producted with u minus v. Also orthogonality, we have the inner product of u and v is equal to 0, means those 2 vectors are orthogonal, and it works both ways. If they're orthogonal, the inner product of u and v is 0. And if the inner product of u and v is 0, that means the vectors are orthogonal. Right? So this is the more generalized version of these concepts coming from dot products, but now we're working with inner products. All right, so let's see an application of these generalized concepts, going back to the cool inner product, where we have the inner product of f and g. And this time we'll do in particular the integral from -1 to 1. So it's like the area from -1 to 1 under the function f times g. Okay, so that's what we're defining to be the inner product. We already showed that this satisfies the 4 properties. So now we're going to use those generalized concepts of length, distance, and orthogonality. All right. So let's look at the inner product of x squared with x. All right, well, that's the integral from -1 to 1 of x squared times x by definition. And that's 0, right? Because we're integrating x cubed. So x to the 4 over 4 is the antiderivative. Plug in 1 and -1, subtract the 2, you get 0. All right, so that's using the fundamental theorem of calculus to figure out the area under that curve. And that means x squared and x are orthogonal to each other, right? Using this definition of the inner product. All right, this idea of orthogonality will become really important later on. Now you can't graph these and look at them and see that they're like perpendicular in a regular geometric sense. It won't work that way, but we'll see this orthogonality property be really helpful later on in an upcoming video. All right, let's look at the length of the function x. All right, well, that'd be the square root of the inner product of x with itself. But the inner product is the integral. And if you calculate that, you'd get the square root of 2/3. So we're calling the length of the function x to have the magnitude square root of 2 divided by 3 by our definition of this inner product. All right. Now if we look at the norm, or the length or the magnitude of the x squared function, right, we do the same thing, but this time we're working with x squared. And so we end up computing this integral and take the square root of it. It ends up being the square root of 2/5. Right? So that's the length of the x squared function. Now the distance between x and x squared, right? That's the norm of x minus x squared, right? But the norm is the square root of the inner product of x minus x squared with itself. So you can compute that integral and figure out that that integral with the square root is the square root of 16 divided by 15. And so that's the generalized idea of distance here between x and x squared using this particular inner product. So there's examples of working with the generalized concepts of orthogonality, length, and distance between two things in our vector space using this generalized inner product that we derived from the idea of a dot product. All right, well, that's it for this video. Thank you.